1. Soil definition and concepts. The science dealing with soil as a natural resource on the surface of the earth, including pedology, soil genesis, classification and mapping, physical, chemical, biological and fertility properties of soil and these properties in relation to their management for crop production. Soil science has 6 well-defined and developed disciplines. 1. Soil fertility, nutrient supplying properties of soil. 2. Soil chemistry, chemical constituents, chemical properties and the chemical reactions. 3. Soil physics, involves the study of physical properties. 4. Soil microbiology, deals with microorganisms, its population, classification, its role in transformations. 5. Soil conservation, dealing with protection of soil against physical loss by erosion or against chemical deterioration, i.e. excessive loss of nutrients either natural or artificial means. 6. Soil pedology, dealing with the genesis, survey and classification. Generally, soil refers to the loose surface of the earth as identified from the original rocks and minerals from which it is derived through weathering process. Soil is a natural body of mineral and organic constituents differentiated into horizons of variable depth, which differs from the material below in morphology, physical makeup, chemical properties and composition and biological characteristics. Composition of soil on volume basis. Soil components: mineral matter, 45% organic matter, 5% soil water, 25% soil air, 25% major component of soil, aura 25% water, 25% mineral particles, 45% organic matter, 5% organism, 10% rules, 10% humus, 80% soil is composed of partly weathered, unwetted, transformed products of rocks, rock minerals and organic matter. The mineral soil consists of 4 major components: phases, mineral material and organic matter, solid, water, liquid, and air, gases. 1. Solid phase, mineral matter. The solid phase is broadly composed of inorganic and organic constituents. The inorganic constituents which forms bulk of solid phase of soil includes silicates, carbonates, soluble salts and free oxides of Fe, Al and Si in addition to some amorphous silicates. Only a small fraction of the solid phase is of organic origin. The sources of organic constituents are 323. 1810. Plant and animals. Of total volume, about half is solid space, 45% mineral matter and 5% organic matter. 2. Liquid phase. Soil water. 40 to 50% of the bulk volume of the soil body is occupied by soil pores, which may be completely and partially filled with water. The soil acts as a reservoir for supplying water to plants for their growth. The soil water keeps salts in solution which act as plant nutrients. Thus, liquid phase is an aqueous solution of salts. 3. Gaseous phase. Soil air. The air-filled pores constitutes the gaseous phase of the soil system. The volume of the gaseous phase is thus dependent on that of liquid phase. The nitrogen and oxygen contents of soil air are almost same as that of atmospheric air, but concentration of carbon dioxide is much higher. The major components of a typical soil exist mainly in an intimately mixed condition. The proportion of these components may vary from time to time and from place to place. The volume composition of subsoil is different from the surface soil. Compared to topsoils, they are lower in organic matter content, lower in total pore space and contain a higher percentage of small pores. This means they have a higher percentage of mineral and water and considerable lower content of organic matter and air. Rocks. The rocks are generally composed of 2 or more minerals. Petrology, Greek, petra means rock, logos means science, deals with science of rocks. It consists of I. Petrography, which deals with description of rocks. 2. Petrogenesis, which is the study of the origin of rocks. Geologists have classified rocks into 3 major groups: igneous, sedimentary and metamorphic. 1. Igneous rocks, Latin ignis, means fire. The whole surface of the earth passed through a molten stage and the first solid mineral was derived from this molten material known as magma. Times igneous rocks are formed by cooling and crystallization of molten material magma on or beneath the surface of the earth. Igneous rocks formed from molten magma that cooling within the earth's crust are called intrusive rocks. The volcanic rocks that cool on the surface of earth are termed extrusive. They are source of parent material for other rocks and ultimately for soils. Times the examples are granite, syenite, diorite, gabbro, dolerite and basalt. 324. 1812. 2. Sedimentary rocks. Sediment is the material that settles on the bottom of something else, usually a liquid. Thus sedimentary rocks are formed from sediments, derived from the breaking down of pre-existing rocks. These are composed of materials that have been worn down by wind, water, or ice and deposited somewhere. Stratification is the most common feature of these rocks and as such these are also termed as stratified rocks. Sedimentary rocks are classified into 3 subgroups: clastic sedimentary, chemical particulates, and organic sedimentary. Clastic sedimentary are simply rock fragments, e.g. sandstone and shale. The second subgroup is sedimentary rocks that are formed from chemical compounds settling out of water solutions, e.g. limestone and dolomite. The last subgroup, organic sedimentary rock, is formed of living or once living substances settling out of water. Coal is a well-known example of an organic sedimentary rock. 3. Metamorphic rocks. The word metamorphic means change in form, and thus metamorphic rocks are those which have undergone some chemical or physical change from its original form. The change due to water is called hydrometamorphism, due to heat is thermometamorphism, and due to pressure is called dynamometamorphism. The examples are gneiss formed from granite, schist formed from basalt or shale, quartzite formed from sandstone, slate formed from shale, marble formed from limestone. Relative abundance of rocks. Composition of Earth's crust as a whole. Igneous rocks, 95%, sedimentary rocks 5%, shales 4%, sandstone 0.75% and limestone 0.25%. Composition of the upper 5 kilometers of the Earth's crust. Sedimentary rocks, shales, 52%, sandstones, 15%, limestone and dolomite -7%, total 74%. Igneous rocks, granite 15%, basalt 3%, total 18%. Others -8%. Note, although sedimentary rocks forms only 5% of the total Earth crust, yet they are important as they occur to the extent of 74%, almost 3/4, at or near the surface of the Earth, upper 5 kilometers. As we go deeper, we find predominance of igneous rocks. Minerals, times the minerals may be defined as naturally occurring, homogeneous element or inorganic compound having definite chemical composition. Times more than 90% of all the minerals in the Earth's crust are made up of compounds containing silicon and oxygen. 325. 1812. There are over 2,500 minerals on Earth. Only 30 minerals are commonly found on the Earth's surface, and in surface rocks most minerals are made from non-living substances. Many have crystal shapes. These are three-dimensional and hence easy to recognize. Minerals are classified into primary and secondary. 1. Primary minerals. The original component of an igneous rock is known as primary mineral. Those primary minerals which are recognized as the characteristic component of that rock are known as essential mineral, while those which occur only in small quantities and whose presence and absence is not so important are called accessory minerals. Olivine Fe, Mg, pyroxenes, Ca, Na, Fe, Mg, amphiboles Ca, Na, Fe, Mg, L, O quartz, feldspars 2. Secondary minerals, a mineral resulting from the decomposition of a primary mineral or from the reprecipitation of the products of decomposition of the primary minerals are called secondary mineral, e.g. clay minerals. Weathering. Weathering is the process of disintegration and decomposition of rocks and minerals, brought about by physical and chemical means, respectively, leading to the formation of regolith, unconsolidated residues of the weathering rock on the Earth's surface or above the solid rocks. Types of weathering. 1. Physical mechanical weathering, disintegration. 2. Chemical weathering, decomposition. 3. Biological weathering, disintegration and decomposition. 1. Physical weathering. Physical weathering is a mechanical process, causing disintegration of consolidated massive rocks into smaller pieces. In this weathering, rock size will be reduced without any change in chemical composition of rock. The agents responsible for physical weathering are the physical condition of rock, changes in temperature, action of water, action of wind and atmospheric electric phenomena. Physical condition of rock. The permeability of rock is probably the most important single factor, which determines the rate at which the rocks weather. Coarse textured sandstone, porous, weathers more rapidly than a fine textured, almost solid, basalt. Unconsolidated fine deposits of volcanic ash weather rather quickly as compared with unconsolidated coarse deposits, such as gravels, which may take much longer, because the water percolates between and not through the gravels. 326. 1812. Temperature. As a result of diurnal temperature changes, the rocks heated during day and cooled during night. Different minerals in polymineral rocks have different coefficient of expansion, and thus heating and cooling of rocks results in differential expansion and contraction of rocks, which eventually produce cracks in rocks, thus facilitating mechanical breakdown. The cubical expansion of quartz is twice as that of feldspars. The dark-colored rocks are subjected to fast changes in temperature as compared to light-colored rocks. Moreover, the temperature of rocks at its surface is very different from that of the part beneath. This creates stress and strain between heated surfaces and the cooled unexpanded parts, resulting in fragmentation of rocks. This process with time may cause the surface layer to peel off from the parent mass and the rock may ultimately disintegrate. This phenomenon is called exfoliation. Water. Of all the agents of physical weathering, the effect of water is more pronounced and widespread. Water acts as disintegrating, transporting and depositing agent. A current moving at a speed of 15 cm, 30 cm, 1.2 m and 9.0 m per second can carry fine sand, gravel, stones, and boulders of several tons respectively. The greater the amount of suspended matter, the quicker will be the disintegration of rocks. Hence the disintegration of rocks is greater near the source of a river than at its mouth. In cold regions, the water in the cracks and crevices freezes into ice, which increases the volume of water by 9%. If the space is not available to accommodate the increased volume, it exerts pressure on rock equivalent to 1465 mgm2, which leads to widening of cracks in huge boulders and dislodging of mineral grains from smaller fragments. In colder regions, the moving glaciers cause great deal of cutting and crushing of bed rocks. Wind has both erosive and transporting effect. Wind, when laden with fine particles, fine sand, silt and clay, has a serious abrasive effect on the rocks. 2. Chemical weathering. Chemical weathering is more complex in nature and involves the transformation of the original material into some new compounds by bringing about alteration in minerals. Chemical weathering takes place mainly at the surface of the rocks. Chemical weathering is highly pronounced in humid tropical regions. Its effectiveness is closely related to the mineral composition of rocks. The plants and animals also contribute directly or indirectly to chemical weathering as they produce O2, CO2, and certain acids that react with earth materials. Various chemical processes are: solution. Water is a universal solvent. Its solubility action is enhanced when it contains dissolved CO2, organic and inorganic acids or salts in it. Most of the minerals are affected by solubilizing action of water, though by varying degrees. When the soluble substances are removed by the continuous 327, 1812 action of flowing or percolating waters, the rock no longer remains solid and develops holes, rills or rough surface and ultimately decomposes. Solubilization of rock minerals under the influence Na, Cl, HO. NaCl plus HOH. CoCo Ca, HCO3, 2CaCO plus H. Cohydration. It is the chemical combination of water molecules with a mineral to form a new mineral. Owing to hydration, the mineral swells, loses luster, becomes softer and tend to fall apart. This is a major chemical weathering process in secondary minerals. 2FeO, hematite, plus 3H2O 2Fe2O3.3H2O, limonite, allo, bauxite, plus 3H2O allo, 3H2O, gibbsite, CaSO4, anhydrite, plus 2HO CaSO4.2HO, gypsum, hydrolysis. Hydrolysis is one of the most important processes in chemical weathering and results in complete disintegration or drastic modification in structure and composition of minerals. It is a major chemical process in primary minerals. Hydrolysis involves the partial dissociation of water into H plus and O ions, which combine with minerals and bring about changes such as exchange, decomposition of crystalline structure and formation of new minerals. The hydrolytic activity of water gets accelerated in the presence of dissolved CO2, minerals and organic acids. In a way, hydrolysis reactions may be considered as the forerunners of the clay formation. Carbonation, combination of carbon dioxide with any base. This effectively decomposes the minerals of rocks and organic matter accelerates this due to more CO2 production. 3. Biological weathering. Unlike physical and chemical weathering, the biological or living agents are responsible for both decomposition and disintegration of rocks and minerals. The biological life is controlled largely by the prevailing environments. Man, animals, higher plants, earthworms, termites and microorganisms are responsible for biological weathering. Fauna, times the disintegration of rocks by cutting action of hills and rocks to build dams, roads etc. by humans. 328. 1813. The animals, insects live in rocks, make burrows and holes in rocks leading to weakening of rocks. Their excreta and other materials lead to chemical decomposition of rocks. Ants and termites build galleries and passages and carries material from lower to upper horizons. Water percolate through the channels and galleries and help in weathering of materials in subsurface horizons. They secrete some acids like formic acid, which aid in decomposition of rocks. Flora. The roots of the plants penetrate into small cracks of rocks. As they grow, they exert disruptive force due to which even hard rocks break into pieces. Some roots grow deep into soil and make open channels for percolation of water into deeper layers. Roots produce acids, which have solubilizing action of constituents of rocks, making them weak. The decomposition of organic matter due to microbial activity also produces several products which play a role in chemical weathering. The physical, chemical and biological weathering processes occur simultaneously in nature. Likewise, different chemical weathering processes occur simultaneously and are interdependent. Soil profile. A vertical section of soil through all its horizons and extending into the parent material. A vertical exposure of the horizon sequence is termed as soil profile. A soil horizon is a layer of soil, approximately parallel to the soil surface, differing in properties and characteristics from adjacent layers below or above it. Soil profile is an historic record of all the soil forming processes and it forms the unit of study in pedological investigations. Practically, soil profile is an important tool for soil classification which is applicable for thorough understanding of the soils. 5 master horizons are recognized in soil profile and are designated using capital letters O, I, E, B and C. Subordinate layers or distinctions within these meta horizons are designated by lowercase letter I, E, I, T, K etc. 1. O horizons, organic. It comprises of organic horizons that form above the mineral soil. They result from litter derived from dead plants and animals. O horizons usually occur in forested areas and are generally absent in grassland regions. 2. A horizon. It is the topmost mineral horizon. It contains a strong mixture of decomposed, humidified, organic matter, which tends to impart a darker color than that of the lower horizons. 329. 1813. 3E horizon. It is an alluviated horizon. Clay and sesquioxides are invariably leached out, leaving a concentration of resistant minerals such as quartz. An E horizon is generally lighter in color than the A horizon and is found under A horizon. 4. B horizon, alluvial. The subsurface, B horizons include layers in which alluviation of materials has taken place from above and even from below. In humid regions, the B horizons are the layers of maximum accumulation of materials such as sesquioxides and silicate clays. In arid and semi-arid regions, CaCO3, CaSO4 and other salts may accumulate in the B horizon. 5. C horizon. It is the unconsolidated material underlying the solemn A and B. It may or may not be the same as the parent material from which the solemn formed. The C horizon is outside the zones of F major biological activities and is generally little affected by the processes that formed the horizons above it. 6. R layer, underlying consolidated rock, with little evidence of weathering. O humus or organic. A topsoil, or horizon surface, more partially decomposed organic matter. A horizon. E alluviated horizon, topsoil, humus, living creatures, inorganic minerals. E horizon, zones of leaching, materials move downward. B subsoil, horizon, subsalt, Iran, aluminium. C parent material, Humic compounds are accumulated and clay leached down from A and E horizons. C. Horizon R. Bedrock, weathered parent material, partial breakdown of inorganic minerals are horizon bedrock. 330. 1813. 3E horizon, it is an elevated horizon. Clay and sesquioxides are invariably leached out, leaving a concentration of resistant minerals such as quartz. And E horizon is generally lighter in color than the horizon and is found under horizon. 4. B horizon, alluvial, the subsurface. B horizons include layers in which alluviation of materials has taken place from above and even from below. In humid regions, the B horizons are the layers of maximum accumulation of materials such as sesquioxides and silicate clays. In arid and semi-arid regions, CaCO3, CaSO4 and other salts may accumulate in the B horizon. 5. C horizon, it is the unconsolidated material underlying the solemn A and B. It may or may not be the same as the parent material from which the solemn formed. The C horizon is outside the zones of F major biological activities and is generally little affected by the processes that formed the horizons above it. 6. R layer, underlying consolidated rock, with little evidence of weathering. O humus or organic. A topsoil, or horizon surface more partially decomposed organic matter. A horizon. E elevated horizon, topsoil, humus, living creatures, inorganic minerals. E horizon zones of leaching, materials move downward. B subsoil, horizon subsalt, Iran, aluminium. C parent material, humic compounds are accumulated and clay leached down from A and E horizons. C horizon. R bedrock, weathered parent material, partial breakdown of inorganic minerals are horizon bedrock. 330. 1814. Two processes and factors of soil formation. Dokuchaev, 1889, established that the soils develop as a result of the action of soil forming factors S is equal to F, P, Cl, O. Further, Jenny, 1941, formulated the following equation: S is equal to F, Ci, O, R, Pt, where Ci environmental climate or organisms and vegetation, biosphere, R relief or topography, P parent material, T time of the action of soil forming factors. Kumar booked the 5 soil forming factors, acting simultaneously at any point on the surface of the earth, to produce soil. Soil forming factors: I passive factors, I parent material, I relief, 3 time, 2 active, 4 climate, V vegetation and organism. 1 passive soil forming factors. The passive soil forming factors are those which represent the source of soil forming mass and conditions affecting it. These provide a base on which the active soil forming factors work or act for the development of soil. I parent material, it is that mass, consolidated material, from which the soil has formed. Parent material as such exerts significant influence on soil characteristics during the initial stages of soil development. The nature of parent material profoundly influences soil characteristics like texture, which is the basic. 331. T 1815, property of the soil and cannot be altered easily. Soil texture controls downward movement of water, thereby affecting the translocation of fine soil particles and plant nutrients. The role of parent material in soil F formation is passive, and so there would be weak correlation between the parent material and soils formed from them. In the initial stages, soil properties are mainly determined by the kind of parent material: basalt red soil, altisoils, basalt black cotton soil, vertisoils, acid igneous rocks, light textured podzolic soils, basic igneous rocks, fine textured cracking clay soils, vertisoils, basic alluvium materials, fine to coarse textured soils, entisoils or inceptisoils. 2. Relief or topography. The relief and topography sometimes are used as synonymous terms. They denote the configuration of the land surface. The topography refers to the differences in elevation of the land surface on a broad scale. Red soils, higher topographic position. Black cotton soil, lower topographic position. Soil formation on flat to almost flat position. On level topographic positions, almost the entire water received through rain percolates through the soil. Under such conditions, the soils formed may be considered as representative of the regional climate. They have normal solemn with distinct horizons. But vast and monotonous level land with little gradient often has impaired drainage conditions. Soil formation on undulating topography. The soils on steep slopes are generally shallow, stony and have weakly developed profiles with less distinct horizonation. It is due to accelerated erosion, which removes surface material before it has the time to develop. Reduced percolation of water through soil is because of surface runoff, and lack of water for the growth of plants, which are responsible for checking of erosion and promote soil formation. 3. Time. Soil formation is a very slow process requiring thousands of years to develop a mature pedan. The period taken by a given soil from the stage of weathered rock, i.e. regolith, up to the stage of maturity is considered as time. The matured soils mean the soils with fully developed horizons, I, B, C. It takes hundreds of years to develop an inch of soil. 332. 1815. The time that nature devotes to the formation of soils is termed as pedologic time. It has been observed that rocks and minerals disintegrate and or decompose at different rates. The coarse particles of limestone are more resistant to disintegration than those of sandstone. However, in general, limestone decomposes more readily than sandstone, by chemical weathering. 2. Active soil forming factors. The active soil forming factors are those which supply energy that acts on the mass for the purpose of soil formation. These factors are climate and vegetation, biosphere. 1. Climate. Climate is the most significant factor controlling the type and rate of soil formation. Directly, Climate affects the soil formation by supplying water and heat to react with parent material. Indirectly, it determines the fauna and flora activities which furnish a source of energy in the form of organic matter. This energy acts on the rocks and minerals in the form of acids, and salts are released. The indirect effects of climate on soil formation are most clearly seen in the relationship of soils to vegetation. Precipitation and temperature are the two major climatic elements which contribute most to soil formation. Precipitation. Precipitation is the most important among the climatic factors. As it percolates and moves from one part of the parent material to another, it carries with it substances in solution as well as in suspension. The substances so carried are redeposited in another part or completely removed from the material through percolation when the soil moisture at the surface evaporates, causing an upward movement of water. The soluble substances move with it and are translocated to the upper layer. Thus rainfall brings about a redistribution of substances both soluble as well as in suspension in soil body. Temperature. Temperature is another climatic agent influencing the process of soil formation. High temperature hinders the process of leaching and causes an upward movement of soluble salts. High temperature favors rapid decomposition of organic matter and increase microbial activities in soil, while low temperatures induce leaching by reducing evaporation and thereby favor the accumulation of organic matter by slowing down the process of decomposition. Temperature thus controls the rate of chemical and biological reactions taking place in the parent material. 2. Organism and vegetation. Organism. Times the active components of soil ecosystem are plants, animals, microorganisms and man. 333 1816. The role of microorganisms in soil formation is related to the humification and mineralization of vegetation. The action of animals, especially burrowing animals, to dig and mix up the soil mass and thus disturb the parent material. Man influences the soil formation through his manipulation of natural vegetation, agricultural practices, etc. Compaction by traffic of man and animals decrease the rate of water infiltration into the soil and thereby increase the rate of runoff and erosion. Vegetation. The roots of the plants penetrate into the parent material and act both mechanically and chemically. They facilitate percolation and drainage and bring about greater dissolution of minerals through the action of CO2 and acidic substances secreted by them. The decomposition and humification of the materials further adds to the solubilization of minerals. Forests reduces temperature, increases humidity, reduce evaporation and increases precipitation. Grasses reduce runoff and result greater penetration of water into the parent material. Pedogenic or soil-forming processes. A soil-forming process may be defined as a complex or sequence of events including both complicated reactions and simple rearrangement of matter which intimately affect the soil. Soil formation is a process of two consecutive but overlapping stages. 1. The weathering of rock, R, into parent material. 2. The formation of the soil from parent material. Soil-forming processes. Rock, parent material, soil. These processes are also known as soil-building processes or pedogenic processes. The basic soil-forming processes involved in soil formation includes the following. 1. Gains or additions of water, mostly as rainfall, organic and mineral matter to the soil. 2. Losses of the above materials from the soil. 3. Transformation of mineral and organic substances within the soil. 4. Translocation or the movement of soil materials from one point to another within the soil. It is usually divided into two aspects. 334 1816. Movement in solution, leaching. Movement in suspension, elevation, of clay, organic matter and hydrous oxides. Soil forming processes. A. Fundamental soil forming processes. B. Specific soil forming processes. A. Fundamental soil forming processes. Humification. It is the process of transformation or decomposition of raw organic matter into humus. It is an extremely complex process involving various organisms such as bacteria, fungi, actinomycetes, earthworms and termites. The decomposition of organic matter takes place in two phases, mineralization and humification. Mineralization is a biochemical breakdown of dead plant tissues by soil microorganisms to produce simple structured soluble organic substances, mineral compounds, metal cations and gases, CO2. During the second phase, that is humification, soluble organic substances regroup themselves into large molecules by polymerization and become poorly soluble. They form major part of soil humus and provide site for retention of cations. The other part of humus is the polysaccharides gummy products of microbial excretions, which help in soil aggregation. The characteristics are influenced by the nature of vegetation residue and the way it becomes decomposed and synthesized into new organic compounds. Elevation, Latin, ex or e out and laver to wash. Elevation means washing out. It is the process of removal of constituents in suspension or solution, clay, Fe2O3, LO, CO2, humus, CaCO3, other salts etc., by the percolating water from the upper to lower layers. The elevation process involves mobilization and translocation of mobile soil constituents resulting in textural differences. Translocation depends upon relative mobility of elements and depth of percolation. The horizon formed by the process of elevation is termed as alluvial horizon, A2 or E horizon. 1335. 1817. Leaching refers to the movement and removal of material in solution from the soil. It connotes the removal of the dissolved material from the entire soil. Elemental mobility Ca2 plus Na plus K plus, Mg2 plus, Fe2 plus, Psi4 plus, L3 plus, most mobile, least mobile, elevation, Latin in, and laver to wash. The process of deposition of soil materials, removed from the alluvial horizon, in the lower layer is termed as elevation. This is the region of maximum accumulation of materials such as iron and aluminium oxides and silicate clays. The horizon formed by this process is termed as alluvial horizon, B horizon, especially Bt. The process leads to horizon of gains and textural contrast between E and BT horizons. Elevation and elevation. O horizon A horizon E horizon exited B horizon back C horizon elevation. Water percolates down soil column, transporting organic material and soluble inorganic matter. Elevation. Materials transported from upper soil horizons are deposited soil particles surrounded by elevated lawns and other material. 336. 1817. B. Specific soil forming processes. The fundamental processes provide a framework for more specific processes like podzolization, Russian, pod means under, and zola means ash. It is the process of elevation of oxide of iron and aluminium, sesquioxides, and also humus under acidic condition, pH 4 to 5, removal of carbonates by organic acids formed by organic matter, and elevation of the silicon in surface horizon. Abundant organic matter, commonly found under forest, cold and humid climate are favorable for the formation of such soils. The elevated horizon assumes a bleached gray color and is left in highly acid, siliceous condition, and the term podzol has been used for such soils. Cool and moist climate, humus-rich times acidic organic litter, elevation of a bases, oxides, sineys, light pale layer sandy, bleached spudic horizon, elevation of bauxites and clays, low pH acyl solution, Vasi loss of base to water tableau. Latrization, Latin, later a brick. The term laterite is derived from the word later meaning brick or tile and was originally applied to a group of high clay Indian soils found in Malabar hills of Kerala, Tamil Nadu, Karnataka, Madhya Pradesh and Maharashtra. Latrization is inverse process to that of podzolization, i.e. the process that removes silica, instead of sesquioxides from the upper layers and thereby leaving sesquioxides to concentrate in the soil. 337. 1817. The process operates under rainforests of tropical areas, warm and humid, tropical, climate and basic parent materials are favorable for such soils. It refers specifically to a particular cemented horizon in certain soils which when dried, become very hard, like a brick. Such soils, in tropics, when massively mixed with sesquioxides, iron and aluminium oxides, to an extent of 70 to 80% of the total mass, are called laterites or latosols, oxysols. Warm and humid climates, very little organic matter, oxic horizon. Residual iron and aluminum. A. Silica, so, removed accumulations of iron, and B. Aluminum plinthite, ironstone, formation food soluble material to water table to streams. Salinization. It is the process of accumulation of salts, such as sulfates and chlorides of calcium, magnesium, sodium and potassium in soils in the form of a salty, salic, horizon. The intensity and depth of accumulation vary with the amount of water available for leaching. It is quite common in arid and semi-arid regions. It may also take place through capillary rise of saline groundwater and by inundation with seawater in marine and coastal soils. Salt accumulation may also result from irrigation or seepage in areas of impeded drainage. Desalinization. It is the process of removal of excess soluble salts from horizons that contain enough soluble salts to impair the plant growth. Drainage is essential for desalinization. 338. 1818. Alkalization, solonization. The process by which soils with high exchangeable sodium and pH 85 are formed. Often sodium carbonate and sodium bicarbonate are formed. In extreme cases the soil colloids become dispersed and tend to move downward. The dispersion results in poor physical condition of the soil. Dealkalization, solidization. The process refers to the removal of Na+ from the exchange sites. This process involves dispersion of clay. Dispersion occurs when Na+ lawns become hydrated. The process is effected by intensive leaching and degradation which takes place in older soils. Calcification. The process operates in arid and semi-arid regions and refers to precipitation and accumulation of calcium carbonate, CaCO3, in some part of the profile. The accumulation of CaCO3 may result in the development of a calcic horizon. Calcium is readily soluble in acidic soil water and or when CO2 concentration is high in root zone as CO2 plus H2O is equal to H2CO3. H2CO3 plus CaCa, HCO3, 2, soluble. Ca, HCO3, 2 is equal to CaCO3 plus H2O plus CO2, precipitates, put at equal to or greater than precip dark color, high in basis O dense sod cover of A interlaced grasses and roots. E calcic horizon. Possible formation of caliche, accumulation of excess calcium carbonate. C. 339. 1818. Decalcification. In regions where some water percolates through the soil profile, decalcification takes place leading to the formation of calcic horizon down below. In humid regions, calcium carbonate reacts with water containing dissolved carbon dioxide to form soluble bicarbonate which may be completely leached out of the soil profile. CaCO3 plus CO2 plus H2O, insoluble, is equal to Ca, HCO3, 2, soluble. Carbonation. It occurs when carbon dioxide interacts chemically with minerals. When carbon dioxide is dissolved in water, it forms weak carbonic acid. When carbonic acid comes in contact with the surface of the earth, it dissolves large masses of limestone, creating caves and caverns. Glaciation. The term glacier is of Russian origin, means blue, grey or green clay. The glaciation is a process of reduction, due to anaerobic condition, of iron in waterlogged soils with the formation of mortals and concretions. Such soils are called as hydromorphic soils. The process is not dependent on climate, high rainfall as in humid regions, but often on drainage conditions. Pedoturbation. It is the process of mixing of the soil. One faunal pedoturbation. It is the mixing of soil by animals such as ants, earthworms, moles, rodents, and man himself. 2. Floral pedoturbation. It is the mixing of soil by plants as in tree tipping that forms pits and mounds. 3. Argillic perturbation. It is the mixing of materials in the soil by the churning process caused by swell shrink clays as observed in deep black cotton soils. 340. 1818. 3. Soil physical properties. The physical properties of a soil play an important role in determining its suitability for crop production. These properties depend on the amount, size, shape, arrangement and mineral composition of its particles. These properties also depend on organic matter content and pore spaces the plant support. Root penetration, drainage, aeration, retention of moisture and plant nutrients are linked with the physical condition of the soil. Some important physical properties of soils are soil texture, structure, density, porosity, color, consistence and soil water. 1. Soil texture. Soil texture refers to relative proportion of mechanical soil separates below 2 mm in diameter, with sand, silt and clay. 3. Size classes are particularly important. 1. Sand, size as in beach sand. 2. Silt, size like talcum powder. 3. Clay, small particles which stick together, like modeling clay. The determination of various sized particles, sand, silt and clay, helps in understanding various soil properties e.g. water retention, cation exchange capacity, soil workability, erodibility etc. The information about particle size analysis is also of utmost importance for judicious nutrient and water management. Particle size classification, S.No. USDA classification. Separate particle diameter, mm, separate particle diameter, mm, very coarse sand 2.0-1.0 coarse sand 2.0-0.2 coarse sand 1.0-0.50.5.0.25 fine sand. Silt medium sand 0.25-0.1 fine sand 0.1-0.05 very fine sand silt clay 0.05-0.002. 2357 International Soil Science Society Classification 0.2-0.020.02-0.002 clay 190 10 clay 80.8888% clay percent silt sandy clay silty clay loam sandy clay loam silt sandy loam silt loam 30 20 10 loamy land sand percent sand 100 Importance of soil texture. Texture has good effect on management and productivity of soil. Sandy soils are of open character, usually loose and friable. Such type of the texture is easy to handle in tillage operations. Sand facilitates drainage and aeration. It allows rapid evaporation and percolation. Sandy soils have very little water holding capacity. Such soils cannot stand drought and unsuitable for dry farming. Sandy soils are poor storehouse of plant nutrients. Contain low organic matter. Leaching of applied nutrients is very high. Times in sandy soil, few crops can be grown such as potato, groundnut and cucumbers. Clay particles play a very important role in soil fertility. Clayey soils are difficult to till and require much skill in handling. When moist clayey soils are exceedingly sticky and when dry, become very hard and difficult to break. Times they have fine pores, and are poor in drainage and aeration. 342. 1819. They have a high water holding capacity and poor percolation, which usually results in water logging. They are generally very fertile soils, in respect of plant nutrient content. Rice, jute, sugarcane can be grown very successfully in these soils. Loam and silt loam soils are highly desirable for cultivation generally. The best agriculture soils are those contain 10 to 20% clay, 5 to 10% organic matter and the rest equally shared by silt and sand and 30% silt called as clay rather than clay loam. Soil with high organic matter content and good structure permits water absorption. Hard-packed surface soil plus impermeable subsoil prevents absorption. Rock layer prevents water from soaking deeply into soil. Figure 3. Soil with good permeability allows water to be easily absorbed. 2. Soil structure. The term soil structure refers to the arrangement of primary and secondary particles into a certain structural pattern. The primary particles are sand, silt and clay whereas the secondary particles are the cluster of the primary particles which are called aggregates and beds. Soil structure greatly influences the amount and nature of porosity and thus influences much soil physical process such as water retention and movement, porosity and aeration, transport of heat etc. 343. 1819. My structure can be modified by cultivation and tillage operations while texture is an inherent property of soil and cannot be modified within short period of time. Formation of soil structure. Soil particles may be present either as single individual grains or as aggregate i.e. group of particles bound together into granules or compound particles. These granules or compound particles are known as secondary particles. A majority of particles in a sandy or silty soil are present as single individual grains while in clayey soil they are present in granulated condition. The individual particles are usually solid, while the aggregates are not solid but they possess a porous or spongy character. Most soils are mixture of single grain and compound particle. Soils, which predominate with single grains are said to be structureless, while those possess majority of secondary particles are said to be aggregate, granulated or clump structure. Mechanism of aggregate formation. The bonding of the soil particles into structural unit is the genesis of soil structure. The bonding between individual particles in the structural units is generally considered to be stronger than the structural units themselves. In aggregate formation, a number of primary particles such as sand, silt and clay are brought together by the cementing or binding effect of soil colloids. The cementing materials taking part in aggregate formation are colloidal clay, iron and aluminium hydroxides and decomposing organic matter. Whatever may be the cementing material, it is ultimately the dehydration of colloidal matter accompanied with pressure that completes the process of aggregation. B. Colloidal clay. By virtue of high surface area and surface charge, clay particles play a key role in the formation of soil aggregates. Sand and silt particles cannot form aggregates as they do not possess the power of adhesion and cohesion. These particles usually carry a coating of clay particles. They are enmeshed in the aggregates formed by the adhering clay particles. Colloidal particles form aggregates only when they are flocculated. There is vast difference between flocculation and aggregation. Flocculation is brought about by coalescence of colloidal partices and is the first step in aggregation. Aggregation is something more than flocculation, involving a combination of different factors such as hydration, pressure, dehydration, etc. and required cementation of flocculated particles. The cementation may be caused by cations, oxides of Fe and Al, humus substances and products of microbial excretion and synthesis. Clay particles form aggregates only if they are wetted by a liquid like water whose molecules possess an appreciable dipole moment. Clay water cation, clay water cation, clay. 344. 1820. The aggregation also depends upon the nature of clay particles, size and amount of clay particles, dehydration of clay particles, cations like calcium and anions like phosphate. C. Fe and Al oxides. The colloidal Fe oxides act as cementing agent in aggregation. Al oxides bind the sand and silt particles. These act in two ways. A part of the hydroxides acts as a flocculating agent and the rest as a cementing agent. D. Organic matter. It also plays an important role in forming soil aggregates. During decomposition, cellulosic substances produce a sticky material very much resembling mucus or mucilage. The sticky property may be due to the presence of humic or humic acid or related compounds produced. Certain polysaccharides formed during decomposition. Some fungi and bacteria have cementing effect probably due to the presence of slimes and gums on the surface of the living organisms produced as a result of the microbial activity. Types of soil structure. Aggregation of soil particles can occur in different patterns, resulting in different soil structures. Based on the shape and arrangement of beds or aggregates, soil structure is classified into four principal types: plate-like, prism-like, block-like and spheroidal structure. 1. Plate-like. In this type, the aggregates are arranged in relatively thin horizontal plates or leaflets. The horizontal axis or dimensions are larger than the vertical axis. Plates often greatly impair water circulation. It is commonly found in forest soils, in part of the A horizon, and in claypen soils. Platy structure is often formed from parent materials and can also result due to compaction of heavy machinery on clayey soils. When the unit's layers are thick they are called platy, and when they are thin then it is laminar. 2. Prism-like. Times in prism-like structure, the vertical axis is more developed than horizontal, giving a pillar-like shape. They are commonly found in the subsurface horizons of semi-arid and arid regions. The prisms having rounded tops are called columnar and mostly occur in subsoils of salt-affected soils. When the tops are flat or level the structure is termed as prismatic. 3. Block-like. The structure is blocky when soil particles cling together in nearly square or angular blocks having more or less sharp edges. T. 345. 1820. The beds have sizes varying from 1 cm to 10 cm. There are two types: angular blocky and subangular blocky. In the former, the edges are relatively sharp, whereas in later the edges are rounded. They are commonly found in the B horizon where clay has accumulated. 4. Spheroidal. Granular. Here the individual particles of sand, silt and clay are grouped together in small, nearly spherical grains. These rounded complexes usually loosely arranged and readily separated. When the beds or aggregates are relatively non-porous, they are called granules, and porous granules are termed as crumbs. They are commonly found in the A horizon of the soil profile. The terms commonly used for the size classes are 1. Very fine or very thin. 2. Fine or thin. 3. Medium. 4. Coarse or thick. 5. Very coarse or very thick. Granular resembles cookie crumbs and is usually less than 0.5 cm in diameter. Commonly found in surface horizons where roots have been growing. Blocky. Irregular blocks that are usually 1.5-5.0 cm in diameter. Prismatic. Vertical columns of sod that might be a number of m long, usually found in lower horizons. Columnar. Vertical columns of soil that have a salt tap at the top, found in soils of arid chmarts. Platy. Thin, flat plates of soil that he horizontally. Usually found in compacted soil. Single-grain soil is broken into individual particles that do not stick together. Always accompanies a loose consistence. Commonly found in sandy soils. 346. 1820. Effect of soil structure on other physical properties. 1. Porosity. Porosity of a soil is easily changed. In plate-like structure, pore spaces are less, whereas in crumby structure pore spaces are more. 2. Temperature. Crumby structure provides good aeration and percolation of water in the soil. Thus these characteristics help in keeping optimum temperature in comparison to plate-like structure. Density. Bulk density varies with the total pore space present in the soil. Structure chiefly influences pore spaces. Platy structure with less total pore spaces has high bulk density, whereas crumby structure with more total pore spaces has low bulk density. 3. Consistence of soil also depends on structure. Plate-like structure exhibits strong plasticity. 4. Color. Bluish and greenish colors of soil are generally due to poor drainage of soil. Platy structure normally hinders free drainage. Importance of structure. Soil structure influences rather indirectly by the formation of an array of pores of various shapes and sizes. These pores are controlling factors governing water, air and temperature in soil. The role of soil structure in relation to plant growth. Soil structure influences the amount and nature of porosity. Structure controls the amount of water and air present in the soil. Not only the amount of water and air dependent on soil structure, but their movement and circulation are also controlled by soil structure. It affects tillage practices. Structure controls runoff and erosion. Platy structure normally hinders free drainage, whereas sphere-like structure, granular and crumby, helps in drainage. Crumby and granular structure provides optimum infiltration, water holding capacity, aeration and drainage. It also provides good habitat for microorganisms and supply of nutrients. Factors influencing genesis of soil structure. The genesis of soil structure refers to bonding of soil particles into structural units or aggregates. In aggregate formation, a number of primary particles such as sand, silt and clay are brought together by the cementing or binding effect of soil colloids. The cementing materials taking part in aggregate formation are colloidal clay, iron and aluminium, hydroxides and decomposing organic matter. 347. 1821. 1. Climate. Climate has considerable influence on the degree of aggregation as well as on the type of structure. In arid regions there is very little aggregation of primary particles. In semi-arid regions, the degree of aggregation is greater. 2. Wetting and drying. It is a well-known fact that alternate wetting and drying produce aggregation. When a dry soil is wetted, the soil colloids swell on absorbing water. On drying, shrinkage produces strains in the soil mass gives rise to cracks, which break it up into clods and granules of various sizes. The breaking of aggregates is due to unequal swelling and compression of the entrapped air. 3. Organic matter. Organic matter improves the structure of a sandy soil as well as of a clay soil. In case of a sandy soil, the decomposing organic matter and the associated microorganisms cement the sand particles together to form aggregates. 4. Tillage. Cultivation implements break down the large clods into smaller fragments and aggregates. For obtaining good granular and crumby structure, optimum moisture content in the soil is necessary. If the moisture content is too high, it will form large clods on drying. If it is too low, some of the existing aggregates will be broken down. 5. Plants, roots and residues. Excretion of gelatinous organic compounds and exudates from roots serve as binding agents. Root hairs make soil particles to cling together. In grassland soils more granulation is observed. Pressure exerted by the roots hold the particles together. Plant tops and residues shade the soil, prevent it from extreme and sudden temperature and moisture changes and also from raindrop impedance. Plant residues serve as a food to microbes which are the prime aggregate builders. 6. Microbes. Growth of microorganisms is responsible for binding together of soil particles and thus increases the soil aggregation. Times algae, fungi and actinomycetes keep the soil particles together by the products of decomposition. Mycelial growth of fungi bind the particles together. 7. Animals. Among the soil fauna small animals like earthworms, moles and insects etc. that burrow in the soil are the chief agents that take part in the aggregation of finer particles. 348. 1821. Soil consistency. Soil consistency is a term used to describe the resistance of soil to mechanical stress or manipulation at various moisture contents. According to Russell and Russell, 1950, soil consistency designates the manifestations of the physical forces of cohesion and adhesion acting within the soil at various moisture contents including the behavior towards gravity, pressure, thrust and pull, tendency to adhere to foreign bodies and the sensations which are evidenced by the fingers of the observer, as feel. Soil consistency is described at 3 moisture levels namely, wet, moist, and dry. 1. Wet soils. In wet soils the consistency is denoted by terms stickiness and plasticity. Stickiness is grouped into 4 categories namely I, non-sticky, 2, slightly sticky, 3, sticky and 4, very sticky. Plasticity of a soil is its capacity to be molded, to change its shape depending on stress, and to retain the shape even when the stress is removed. Soils containing more than 15% clay exhibit plasticity, pliability and the capacity of being molded. There are 4 degrees in plasticity namely I, non-plastic, 2, slightly plastic, 3, plastic and 4, very plastic. 2. Moist soil. Moist soil with least coherence adheres very strongly and resists crushing between the thumb and forefinger. The different categories are I. Loose non-coherent, 2. Very friable coherent, but very easily crushed, 3. Friable easily crushed, 4. Firm crushable with moderate pressure, V. Very firm, crushable only under strong pressure and 6. Extremely firm, completely resistant to crushing. Type and amount of clay and humus influence this consistency. 3. Dry soil. In dry soil, the degree of resistance is related to the attraction of particles for each other. The different categories are loose non-coherent soft breaks with slight pressure and becomes powder slightly hard break under moderate pressure hard breaks with difficulty with pressure very hard very resistant to pressure extremely hard, extreme resistance and cannot be broken. 349. 1822. Why? Management of soil structure. Soil structure management aims at the improvement and maintenance of soil structure, which are the major challenges in cultivated lands. The general principles relevant to structure management are tilling soils at optimum moisture conditions to ensure least destruction of soil structure. Suitable tillage and minimum tillage practices to minimize the loss of aggregate stabilizing organic substances, covering soil surface with organic materials, mulch, to mitigate the beating action of rain and to add organics to soil. Incorporation of crop residues and animal manures into soil, which upon decomposition, would stabilize soil aggregates. Suitable cropping systems, application of phosphatic fertilizers, inclusion of grasses and sod crops in the rotation, would enhance organic matter and favor stable aggregation. Green manuring and cover crops are good sources of organic matter. Times use of synthetic organic amendments or soil conditioners. Difference between soil texture and soil structure. Basis of comparison. Soil texture. Soil structure. Soil texture can be determined using qualitative methods such as texture by feel and quantitative methods such as hydrometer method. Soil structure is determined by how individual soil granules clump, bind together and aggregate, resulting in the arrangement of soil pores between them. Description. Soil texture and its clay content influence the amount of air in the soil and its water holding capacity. Soil structure has a major influence on water and air movement, biological activity, root growth and seedling emergency. Influence. Soil texture is classified based on the percentage of sand, silt and clay in the soil. Soil structure can be classified into the following types: platy, prismatic, columnar, blocky, granular, wedge and lenticular. Classification. Soil texture has agricultural applications such as determining crop suitability and to predict the response of the soil to soil structure has agricultural, biological and geological applications such as determination of soil properties, solute transport, environmental and management processes, soil management, etc. Application. 350. 1822. Conditions such as drought or calcium requirement. Factors with influence. Soil structure is influenced by the relative and clay percentages of sand, silt in the soil. Factors that influence soil structure include tillage, wheel traffic, roots, biological activities in the soil, rainfall, wind erosion, shrinking, swelling, freezing and thawing. 3 densities of soil. Bulk density is the ratio of the mass of dry solids in a medium to the volume of the medium. It involves the measure of the mass of the entire volume of a soil sample. The density is a major factor in dealing with root movement and stability of the soil. The bulk density of a soil is always smaller than its particle density. The bulk density of sandy soil is about 1.6 GCM superscript 3, whereas that of organic matter is about 0.5. Bulk density normally decreases as mineral soils become finer in texture. The bulk density varies indirectly with the total pore space present in the soil and gives a good estimate of the porosity of the soil. Bulk density is of greater importance than particle density in understanding the physical behavior of the soil. Generally, soils with low bulk densities have favorable physical conditions. Textural class: sandy soil, clay, bulk, GCC, 1.6-1.4 density pore space, %. Porosity, 40-47. Particle density is the ratio of the mass of solids to the volume of the soil solids. It is determined largely by the texture. Particle density involves the measure of the mass of only the solid particles in a soil sample. Generally, particle density of normal soils is 2.65 grams per cubic centimeter. The particle density is higher if large amount of heavy minerals such as magnetite, limonite and hematite are present in the soil. With increase in organic matter of the soil, the particle density decreases. Particle density is also termed as true density. Coarse sand, 2.655 GCM superscript 3, clay 2.837 GCM superscript 3. Soil texture affects bulk density. Different separates have different masses and have corresponding pore space. Soil structure also determines density because various soil arrangements compact more easily than others. 351. 1822. Factors affecting bulk density. 1. Pore space. Since bulk density relates to the combined volume of the solids and pore spaces, soils with high proportion of pore space to solids have lower bulk densities than those that are more compact and have less pore space. Consequently, any factor that influences soil pore space will affect bulk density. 2. Texture. Fine textured surface soils such as silt loams, clays and clay loams generally have lower bulk densities than sandy soils. This is because the fine textured soils tend to organize in porous grains, especially because of adequate organic matter content. This results in high pore space and low bulk density. However, in sandy soils, organic matter content is generally low, the solid particles lie close together and the bulk density is commonly higher than in fine textured soils. 3. Organic matter content. More the organic matter content in soil results in high pore space, thereby shows lower bulk density of soil and vice versa. Bulk density and particle density importance. Bulk density and particle density are important in the production of crops. The amount of pore space decreases with higher soil density. As a result, soil aeration and water holding capacity decrease. This decrease in water holding capacity is especially significant in the larger pore spaces that are readily available to hold water that plants can utilize. Erosion can also be affected by density. Water that is slow to infiltrate the soil stays in contact with the topsoil for a longer period of time, thereby increasing the rate of erosion. Flooding will result from excessive runoff and decreased infiltration in wet years. Puddling can result from localized compaction, as is the case in tractor tire ruts. The production of containerized crops is influenced by bulk density. Light bulk density eases handling and shipping of potted plants. High or heavy bulk density is needed to provide support for plants. For potted plants, the growing medium's bulk density should be light enough to ease handling and heavy enough to support the plant. 352-1822. Calculating bulk density and particle density. Bulk density 1.321 cubic centimeter, 1.0 centimeters to calculate, volume 1.0 centimeters, solids and pores. Mass 1.32 g cleaved solids only, bulk density mass of dry so volume of sale, solids and pores, bulk density 1.32 10 1.32 gbm. Particle density 1.32 g 1 cubic centimeter, 1.0 centimeters, to calculate, volume 0.5 ohm, splits only mass 1.32 g, Slave solids only, particle density mass of solids volume of solids particle density is equal to 1.322.64 gcm superscript 30.54. Porosity. Soil porosity refers to that part of a soil volume that is not occupied by soil particles or organic matter. The pore space of a soil is the space occupied by air and water. The amount or ratio of pore space in a soil is determined by the arrangement of soil particles like sand, silt and clay. In sandy soils, the particles are arranged closely and the pore space is low. In clay soils, the particles are arranged in porous aggregates and the pore space is high. Presence of organic matter increases the pore space. Factors influencing pore space. 1. Soil texture. Sandy surface soil, 35 to 50% medium to fine textured soils, 50 to 60% compact subsoils, 25 to 30% 2. Crops. Vegetation. Some crops like bluegrass increases the porosity to 57.2% from the original 50%. Cropping reduces the porosity as cultivation reduces the organic matter content and hence decrease in granulation. 353.18.24. Virgin soils have more pore space. Continuous cropping reduces pore space than intermittent cropping. More the number of crops per year, lesser will be the pore space, particularly macropores. Conservation tillage and no tillage reduces porosity than conventional tillage. 3. Size of pores. 1. Macropores, non-capillary pores diameter, 0.05 mm. 2. Micropores, capillary pores diameter. In macropores, air and water moves freely due to gravitation and mass flow. In micropores, the movement of air and water is very slow and restricted to capillary movement and diffusion. Sandy soil have more macropores and clay soils have more micropores. So in sandy soils, water and air movement is rapid due to macropores though the pore space is higher, and in clay soils the air and water is slower due to micropores though the total pore space is higher. Loamy soils will have 50% porosity and have equal portion of macro and micropores. Significance and manipulation of soil porosity. The bulk density and pore space are interrelated. Development of low bulk density values also means the development of large amount of pore spaces. In nature, low bulk density values are usually found in soils with high organic matter contents. High biological activities are necessary for formation and large accumulation of organic matter. Together with the effect of soil organisms, the high humus content will encourage aggregation, increasing in this way soil porosity, and thereby decreasing bulk density values. The cultivation effect of the soil macro and microfauna produces an intricate system of macropores, which is a major factor for lowering the bulk density of soil. Continuous cropping is noted to decrease the amount of organic matter in soils, and is expected to decrease soil aggregation. Tillage by plowing is designed to increase the pore space in soils, but is in fact decreasing organic matter. To alleviate these problems, conservation tillage and no tillage have been introduced. Though many claimed that this increased the organic matter, the latter have not always increased the total pore space. 5. Soil color. The color of the soil is a result of the light reflected from the soil. Soil color is an easily observable soil property and gives an immediate indication of the soil condition. Soil color is inherited from its parent material and that is referred to as lithochromic, e.g. red soils developed from red sandstone. Besides, soil color also develops during soil formation through different soil forming processes and that is referred to as acquired or pedochromic color e.g. Red soils developed from granite, gneiss or schist. 354. 1825. Significance. Soil color gives us a clue regarding the drainage condition of the soil, amount of organic matter present and type of parent material from which soil has developed. In general, the dark-colored soils are considered fertile and rich in organic matter. The mottlings when present in lower horizons of a profile indicates poor drainage conditions. Iron compounds in various states of oxidation and reduction are major coloring agents of subsoil horizons. The color of soil containing iron oxides varies from red and rust brown to yellow depending on the degree of hydration. Reduced iron normally displays a green-blue tinge. Soils in anaerobic conditions, such as those in poorly drained depressions, will normally have dull, grey horizons. Alternatively, aerobic soils have bright reddish-brownish colors. Factors affecting soil color. 1. Parent material composition. Soils containing higher amount of iron compounds generally impart red, brown and yellow tinge color. The red color of the soils is due to unhydrated iron oxide. It indicates that the soils are old and more weathered. The yellow color in the soil is due to iron oxide, limonite, and more moist conditions. Due to presence of large amounts of silica and lime or both in the soil, the color of the soil appears like white or light colored. In case of black cotton soils, the black color is due to titaniferous magnetite. Such soils may have less organic matter but still they are black in color. Thus the parent material has direct bearing on the color of the soil formed from it. 2. Soil moisture. Times a well-drained soil will have normal colors as compared to a poorly drained soil. The poorly drained soil will show the sign of graying due to anaerobic or reduced conditions. When soils are waterlogged for a longer period, the permanent reduced condition will develop. The presence of ferrous compounds resulting from the reducing condition in waterlogged soils impart bluish and greenish color. During monsoon period due to heavy rain the reduction of soil occurs and during dry period the oxidation of soil also takes place. Due to this alternate oxidation and reduction, due to alternate wetting and drying, some colored patches develop. These patches are known as mottles. This mottled color is due to residual products of this process, especially iron and manganese compounds. The background soil surface is known as matrix. The matrix and mottle color are recorded separately. 355. 3D 1825. 3. Organic matter. Soils containing high amount of organic matter show the color variation from black to dark brown. In forest soils and grassland soils, more organic matter is added to the soil every year. This makes the soil darker in color. In hot and dry regions, the organic matter is readily decomposed and lost. Hence, these soils are lighter in color. Thus, organic matter is important color imparting constituent in soils. Determination of soil color. The soil colors are determined by using Munsell color chart. In this chart, different color chips are systematically arranged by three variables, namely hue, value and chroma. Hue it indicates the dominant spectral color, red, yellow, blue and green. Value it indicates lightness or darkness of a color, the amount of reflected light. Chroma, it represents the purity of the color, strength of the color. Hue term missile soil color. Name diagram Munbel sun color chart pink pink radish yellow light brown brown strong tone dark brown gray black very dark brown 12. 356. 1826. 6. Soil water. Importance of soil water. Soil water serves as a solvent and carrier of food nutrients for plant growth. Yield of crop is more often determined by the amount of water available rather than the deficiency of other food nutrients. Soil water acts as a nutrient itself. Soil water regulates soil temperature. Soil forming processes and weathering depend on water. Microorganisms require water for their metabolic activities. Soil water helps in chemical and biological activities of soil. It is a principal constituent of the growing plant. Water is essential for photosynthesis. Water serves four functions in plants. It is the major constituents of plant protoplasm, 85 to 95%. It is essential for photosynthesis and conversion of starches to sugars. It is the solvent in which nutrients move into and through plant parts to capture sunlight. In fact, the soil water is a great regulator of physical, chemical and biological activities in the soil. A representative cultivated loam soil contains approximately 50% solid particles, sand, silt, clay and organic matter, 25% air and the rest 25% matter. Only half of this water is available to plants because of the mechanics of water storage in the soil. Structure of water. Water can participate in a series of reactions occurring in soils and plants, only because of its structural behavior. Water is simple compound, its individual molecules containing one oxygen atom and two much smaller hydrogen atoms. 8 hydrogen band covalent bond 8 H100 and 4.5 dipole moment H8. 357. 1826. Factors affecting soil water. 1. Texture. Finer the texture, more is the pore space and also surface area, greater is the retention of water. 2. Structure. Well aggregated porous structure favors better porosity, which in turn enhance water retention. 3. Organic matter. Higher the organic matter, more is the water retention in the soil. 4. Density of soil. Higher the density of soil, lower is the moisture content. 5. Temperature. Cooler the temperature, higher is the moisture retention. 6. Salt content. More the salt content in the soil, less is the water available to the plant. Classification of soil water. Soil water has been classified from a soil moisture tension at gravitational state. 2. Capillary water. Capillary water is held